What I'd like to discuss in terms of your exam review for this video is the capstone problems. And basically what a capstone problem is it requires you to use knowledge you gained throughout the course to solve a unique problem. So it's not kind of confined to one unit. It kind of uses a range of things. Often there's some new information that's presented that you have to kind of use and use your understanding of the physics that you learned in the course to kind of help solve this problem. I have 5 sample problems posted on the course, and I'll pick one of these to do. Let's look at, okay, so I'll do this one here, the one that's a 3.2 kilogram metallic ball. I have used this one in the past on an exam. It's a rather long question. This was actually a culminating task problem. So you won't get something this large, but this is still something that's doable. So let's try to solve this. And the first thing to do when you're approaching a problem like this, just as you approach many problems, let's write down what our given information is. We know that this is a 3.2 kilogram metallic ball. We know the charge of the ball is 5.5 c, so that's a really large charge. We know that its initial velocity here, it's traveling in a vacuum at 7.3 meters per second, and we're given directions of south, 27 degrees east. And it enters this magnetic field that's directed north to south. And the magnetic field, its width, so I'm just going to put W here. Its width is 15 meters wide as measured from east to west. So the situation, as you can imagine, we have a metallic ball. It's floating through a vacuum, or it's traveling through a vacuum. Consider this space, for example. It's moving at a certain direction and it's moving at a certain velocity. We need to figure out, and then it enters this magnetic field, and we need to figure out in what direction will it travel. So this is kind of broken up as it should be A, B, C, D. It looks like it's A, B, A, C. But we should solve this in order because it's actually going to help us to get to the final solution in the end. The first part asks, in what direction will the ball travel due to the magnetic field? So we need to use one of our right-hand rules to figure this out. And if you if you recall, for the right-hand rule, when we're looking at where the excuse me, where the force will be applied, if our magnetic field is directed east to west, so this is my east, this is my west, so my magnetic field is directed in this direction. I'm just going to slide this over so we can see it. We're traveling south at a certain angle towards the east. So let's just draw something like this. This is our general direction of travel. That's our V. The east direction will not interact with the magnetic field because they're parallel. It's traveling to the east. The field's directed to the west, so it's parallel. But what we do know is that this south travel is the direction of our electric charge. And our magnetic charge is directed towards the west here. So in which direction will the ball travel due to the magnetic field? It's either going to travel up or down. So using our right-hand rule, I'm not going to show this, but your index finger rather, it will be your direction of the motion of the ball. Your thumb will be the orientation of the field, so you're going to point your thumb towards the west. And the only way that your middle finger can point would be down in this case. So our, and in this case it would be into the page. So that's into the page. That's our force. So in this case, that's our magnetic force actually. In this case, we would be going down. So part A of this problem, the answer is that the ball will travel down due to the magnetic field. Now it will still travel south and east with this velocity, but the force that's acting on it's going to push it down. So let's look at the next part of this question. For B, we're adding a new variable. We're adding that the magnetic field is 0.1 Tesla. How far will the ball travel in the direction stated in A? Oh, that's why it said that. In A while it is in the magnetic field. So if this is our magnetic field strength, what we need to do is we need to look at how do we calculate our FM. So I'll just hide this for now, and I'll slide something up here. If we remember on our formula sheet, your FM equals QVB sine theta. So using that formula, FM equals QVB sine of theta, what we know is that now what we're trying to do is find the force first, and then we could find out how far the ball travels while it's in this field. So FM equals Q, which is 5.5, V, which is 7.3, B, which is 0.1, and then sine of theta, in this case, it is 27 degrees. So that would be, if we're looking back here, this angle, it's south 27 degrees to the east. This is our 27 degree angle. So we're angled at 27 degrees. So our magnetic force will be what we find out here, 5.5 times 7.3 times 0.1 times sine of 27. And it's 1.8 newtons. I'm going to save this in my memory here. 1.8 to 3 newtons. I'm going to keep it there because that's just an intermediary answer or solution. Now, that's just my force going down. I don't know how long this force is going to act. I can't figure out what our acceleration will be, though. So let's find the acceleration using F equals ma, A equals F over m. So in this case, A equals the 1.823 over our mass, which is 3.2. So I take this value here, divide it by 3.2, and I have my acceleration. So I'm going to store this value now. And I'll write it with 3 decimal points. 0.570 meters per second squared down. So now I know my acceleration. Going back to our givens, this field is 15 meters wide, as measured from east to west. Oh, you know what? I did this a little bit wrong because the magnetic field is directed north to south. Okay, I'm going to continue the problem like this. You can redo it the proper way. I read it a bit wrong. So if I did it that way, then we'd have to say that it's going from north to south. But the basic idea here is that it's 15 meters. After 15 meters of travel in the south direction, we would be out of this magnetic field. So I've kind of had to change this problem around. So what I'm trying to do now, just to make it consistent, otherwise it's not solvable, I've already started and I don't want to redo it, north to south, change that from to east to west, and where it says east to west, change that from north to south. So we're just kind of swapping what our problem says. So now the general idea here is we're going to be traveling for 15 meters through this field in the north-south direction. So we need to see how long we are in this field. So in this case, we're looking at a kinematics problem where we have a velocity, an initial velocity of 7.3. Actually, this is a rather simple problem because the initial velocity is equal to the final velocity. So we just have a velocity of 7.3 times the, we're going in the south direction. So looking back over here, the south direction would be the cosine of that 27. So 73 cosine 27 degrees. This is our direction. Our distance to travel is 15 meters. Our time is not known. So then we have to use the really simple equation. I'll just show it up on here on the screen again. V equals d over t, because our acceleration is 0 in that direction. So V equals d over t. Rearranging that for t, we get d over v, which is 15 over 7.3 cosine of 27 degrees. So this becomes 15 divided by 7.3 divided by cosine of 27 degrees. We have a time of 2.306 seconds that it's in this field. So it's only going to experience that force for 2.306 seconds. So it'll only experience this acceleration for 2.3 seconds. Now, its initial velocity in the up-down direction. So let's look at our givens in this case. The initial velocity in the up-down direction is 0 meters per second. I have my time, I have my acceleration. The question asks how far it will travel. So d is what we need to know. So again, looking at my equations on the other side of this sheet, I have my, the only thing I don't have is my v2. So I have my d that I need to solve for. Vi I have, which is 0. I have my t, I have my a. So it's basically this equation here. So that becomes, solve it up here, d equals vi t plus at squared over 2. This whole thing becomes 0 because my vi is 0. D equals my a, which is 0.570 times my t squared, which is 2.306 squared, divided by 2. So I have my t. I'm going to square that. I'm going to multiply that by my a, and I'm going to divide that by 2. I have a distance traveled of 1.515 meters, and I have to report this using 2 significant digits. D equals 1.5 meters. So that's my answer for B. Now let's go back to our question again. What is the magnitude of the ball's total displacement? So now this one's a little bit more complicated. So if we're talking about the magnitude of the total displacement, this is our dz. That's our d in the up-down direction. And it said the total displacement as it leaves the magnetic field. So our d y is 15 meters because that's how long it was in that field. But we need to see how far it goes to the east-west direction. And then we have to do some trigonometry in 3 dimensions here. So let's find our let's do it on the side here. Let's find our dx. Dx equals vt, so vxt. My t was the 2.306. My v is 7.3 sine of 73 degrees. Sorry, 27 degrees. And my t again was 2.306. So to solve for this, 2.306 times 7.3 times 27 sine. I travel in the x direction 7.6 well, we'll just say 7.6, keep the two significant digits, meters. Now, how far do I travel in all of those displacements? If you think about this in 2 dimensions, we have an x distance of 7.6 and a y distance of 15. This tells me my distance traveled in the xy. And then I have to, so once I solve for that, I have to create another right angle triangle. So let's do this quickly. 15 squared plus 7.6 squared. And I have to find the square root of that. This is 16.8 meters. Then I have to do another triangle. So this is my 16.8 meters. It doesn't really matter the direction I draw this, because in the end I'm going to find my solution if I just do the Pythagorean theorem twice. So this squared plus 1.5 squared, finding the square root of that, I end up with 16.9 meters. So that's my total displacement. So all of this work here would be one capstone problem. This is why they're worth 10 marks. And there is lots of opportunity to get part marks for a question like this. So feel free to try your best to do whatever you can on them. I will make another video solving another one of these problems. I'll just pick another random one, and I'll post that as well.